Okay, Bismillah ar-Rahman ar-Rahim. Salatu wassalamu ala Sayyidina Muhammad. Assalamu alaikum everyone. So, today inshallah we're going to be looking at Lyapunov's direct method. So this method, we're going to be using it to analyze the stability of mechanical systems. Not on its own, so that's why we're going to have two lectures here. So Lyapunov's direct method, in the way that we're going to be doing it, will actually have a limitation. We're going to be doing it tomorrow, next lecture inshallah. And we're going to be fixing it using another theorem that both of them together actually, you're going to find that stability of mechanical systems becomes really very, very easy actually. And more on that later. But today inshallah we're going to be looking at Lyapunov's direct method. If you took any course on nonlinear analysis or adaptive control or any of these courses, actually this is a very fundamental topic. And we're going to be focusing also on the geometric aspect of these computations. In the end, it's very easy to do computations with it. However, when we add the geometric stuff, this actually will make it a little bit interesting. So let's start with a recap. As usual, today we're going to have a case study for the pendulum. So the pendulum will be our prototypical toy example that we're going to be illustrating the concepts. However, this also is valid for different state space models we're going to be discussing later. And then we're going to be looking at a little bit on introduction just to the Lyapunov method and the positive difference functions definitions. So we said that a linear dynamic system can be represented by differential equations of this form that we call the state space model. X is the state, use the control input, Y is the output that you use for observation. F of x, g of x, and h of x are nonlinear functions in general that describe the evolution of the system. We're not looking at any constrained system. You see, we're looking at ordinary differential equations, not differential algebraic equations. So we assume, for example, if we have a manipulator that we already did the reduced modeling. So we're looking at, in the end, the equations of the reduced equations of the manipulator. The control input, usually we design it either for stabilization / regulation. So regulation and stabilization are two names for the same thing, or for tracking or for interaction. So interaction is usually for robotic systems, so it's very particular to robotic systems. Tracking can be, in general, for any type of system, the same for stabilization. This is the topic of what we're going to be doing later on, using the Lyapunov method we're learning today. And usually the design of the controller itself, okay, is intertwined with the process of analyzing the stability of the system. So whenever you see a system f(x) dot equal to f of x, you can either think of it as either the system alone that you want to control without the control input, what we call the open loop system, or the system that you want to control along with a proposed structure for the controller. So you already chosen, for example, that you want the controller to have some sort of function, beta here, as a function of the output, which is already another function of the state, as per the state space model. And then we want to analyze the stability of this system, but when we're analyzing the stability of the system, we're actually at the same time designing the controller. So both of them are actually intertwined together, and more on that later. And then we looked at state space models. We said that for mechanical systems in particular, we usually choose the state to be some configuration-like variable and some velocity-like variable. So if when the mass spring damper system, we haven't looked at it, but this will be part of what we're going to be doing in the assignment. And we looked at the simple pendulum, the N-link manipulator, and for example, the multi-rotor aerial vehicle. A special case of the MAV example we looked at last time is a satellite, which only evolves in rotation, so there's no gravity, there's no full configuration. And another simple example of the N-link manipulator is actually the mass spring damper system, when we just add friction and spring stiffness and so on. There is a recurrent theme here is that the state space of mechanical systems is usually the tangent bundle. Whenever you combine the configuration variable and the velocity, and some velocity-like variable, usually this space that you're thinking about or you're modeling the state space in is actually isomorphic to the tangent bundle. Okay? You can also do it in another way, which is we're going to be looking at it. I don't remember at which point, but sorry.
For the multi-rotor aerial vehicle,
yeah,
the state will be the twist and the H, which is
the pose of the rope.
Yes. How about the wrench?
The wrench is not a state. The wrench will be, if you go back to the equation of motion, the wrench will be the control input, exactly. Yes. And it will enter not in an equation that affects the h dot. So for example, the wrench does not affect the h dot. H dot is an equation for the kinematics, right? The wrench affects the dynamic. So it affects the second equation. So if you go back here, you're going to find actually that the forces, and this is by the way in general mechanical systems. You remember when we had kinematics and dynamics? Kinematics, we don't talk about forces. So usually the first equation in the x dot, so x1 dot is always going to be kinematics. x2 dot, if x2 is velocity, then x2 dot will be something related to acceleration, and this is where the forces usually come to place. Forces and torques and wrenches, depending on which type of system you're talking about. Does that answer your question? Okay. Another way that you can actually model these systems is not on the tangent bundle, but on the what's known as the cotangent bundle. And we said that the tangent bundle would have velocities and would have configuration and velocity, but the cotangent bundle, does anyone remember what kind of variables it will have? The cotangent bundle? It's not the cotangent for the position and the cotangent for the velocity, no. It will also have the same configuration variables. The configuration variables are the same, but instead of the velocities here, the velocity-like variables, what will be there? Something like it? No. Something of the same nature as the forces, or as the, sorry?
No.
Something like the same nature. That will be the state here. Any guess? It will be momenta. So position and momenta, you remember the momentum is a covector, same as the wrench. So actually positions and momentum, so pose and momentum, position and momentum will always be what lives in the cotangent bundle. Okay, we're going to come back to that later. You're going to also see some examples like this in the assignment, so don't be suspicious. Why are we talking about momenta at that point? But this is the relation. Okay. We also looked at the geometric nature of this equation, x dot equal to f of x. We said that in the Euclidean case, you just think of f as some map from Rn to Rn, so it eats Rn n variables, x1 up to xn, and it will spit back x1 dot and x2 dot and up to xn dot. However, in the geometric picture, it's actually a map from the space, and at every point it will give you a vector. It will give you some direction into which the dynamics will flow along. And if you actually start from this point as the initial condition, you see that the trajectories the system will take will always be tangent, okay, to this vector field given by the f of x is actually tangent always to the trajectories you follow. Yes.
Like, can you go to the previous slide? And
Yes.
In the multi-rotor rear view.
Yeah.
The twist here is not the direct. Here it's psi and psi dot,
Yeah.
theta and theta dot.
That's right.
But here in the Bose twist, it's not the direct.
It's not the rate of change of r, so it's not r and r dot or h and h dot. That's what you're saying, right? Any answer to that? Yes.
Because we are interested in the twist and they are related with the map.
It's an isomorphic, right? If you give me the v, I can give you h dot. Or if you give me h dot, I can give you the v. They are isomorphic to one another. The same for the r and the r dot and omega. They are isomorphic to each other.
I think the follow-up question, can you model it with h and h dot?
Yes, of course.
But it's not, the output will not be of use.
No, the equation will be very easy. You all know about it. Actually, it's the Euler-Lagrange equation,
Okay.
but it's horrible. It's horrible to work with. It's not as easy as the one that we had. The equation that was in terms of v dot is actually called the Euler-Poincare equation. It's not called the Euler-Lagrange. Why not the Euler-Lagrange? Because it's not an h and h dot. If you actually write it in h and h dot, it will be very bad. Because, for example, the Euler-Lagrange, you always have second derivative of the position, right? What is the derivative of h dot? H double dot. So if h dot was actually a tangent vector, how do you take the derivative of that?
The derivative of the tangent of the tangent.
So you see, things will get a little bit messy. Yes, exactly.
But it will be an indirect relationship between them.
It will be a messy relationship, actually. So actually, you can write it in coordinates, but and things will get very messy. But to actually, if this is isomorphic, if h dot is isomorphic to v, and the equation of v dot is easier to work with, why not work with? That's the idea. Okay. Any questions? Okay. And then we start talking about, okay, the reason why we're going to be looking at, the way we're going to be doing the stability of systems is that we're not going to simulate the system. We're not going to be simulating it in different conditions and looking at what happens. We're not going to be evaluating the trajectories of the system. We're going to actually be trajectorying f of x. Just by looking at the structure of it, we can say a lot about how the system behaves. And the first thing we said about is that equilibrium points of the system are usually defined as they are the points on the manifold that satisfy f of x equal to 0. So if these are any points that you plug them in the dynamics, you get x dot equal to 0. So if you start at them, you remain at them. Okay? And if you start near them, what happens? Not necessarily. And this is where we said about different notions of stability. If you start near them, and this is the idea of being, it depends on the equilibrium point itself. These are properties of the equilibrium point, and we call these notions stability notions. So all of these equilibrium points, they behave differently. Some of them, you start near them, and you stay in, you start just keeping going back and forth around this equilibrium point. Some other equilibrium points, you start near them, and then you diverge. Some other points, you start near them, and then you converge to the point. So after, as t goes to infinity, you just go to that point and you stay there. And some other points, they are globally asymptotically stable. So the notions we just mentioned are stable, unstable, locally asymptotically stable. So locally means that you start in a small region. This region, by the way, small and close, is not actually properly defined. It's just what you get from it's an intuitive definition. Formally or mathematically defining is actually a hard problem. It's not that easy, but you get the idea. Globally is easy. So globally means that you start anywhere in the state space, you converge to that point. Okay. And let's make all of these concepts, all of these abstract concepts concrete by looking at the pendulum. So the pendulum, these are the equations of motion we looked at last time. So the first equation, x1 dot is equal to x2, is just simply the rate of change of position is equal to velocity. And the second equation is the rate of change of velocity, which is the acceleration is equal to forces divided by mass. Okay? Or because this was a pendulum, so actually it was torques divided by inertia. So you see here we had ml squared here plays the role of the inertia. So these were the friction torques, these were gravity torques, exactly, no, the gravity torque. Okay, so G here was the gravity. And x1 is theta and x2 is theta dot. So first question, you might want to, when you're studying the stability of this system or analyzing its properties, just look at the equilibrium points. It's always the case. So this is the f of x, set it to 0 and solve for it. That's it. As easy as this. So you're just doing algebra. The first equation has to, so f of x is a tuple of numbers. So if it's equal to 0, then all of its different functions need to be 0. So I have two separate functions here. x2 is equal to 0, and all of this is equal to 0. First equation is trivial. x2 is equal to 0, so I already know. Any equilibrium point of that system must have, and what is x2?
Speed.
Velocity. So velocity equal to 0. Makes sense, right? The system, if I start there and has velocity equal to 0, then okay, it makes sense that I'm not going to be moving on. But what about x1? So now we solved half the problem, so we know that all of x2 has to be 0, if this is an equilibrium point. But what about x1? Now if we take x2 equal to 0 and we plug it in here, then you see that this term pops out, and then we're just left with the gravity term, so g over, so this is equation, so go a little bit, point back, so this is the first function equal to 0, second function equal to 0, and now since x2 equal to 0, then the gravity term, the gravity torque should be equal to 0. G and L are constants. Okay, so you just in the end you want to solve sine of x1 equal to 0. Okay, how many solutions does sine x1 equal to 0 have? Infinite numbers, right? They are all multiples of pi. So pi, 2 pi, 3 pi, so on. But not only that, also minus pi, minus 2 pi, and so on and so forth. Okay. So how many equilibrium points does this system have? It has an infinite number of equilibrium points. Does that make sense? Completely doesn't make sense. Why?
Because it should be stable at the base.
If independent of the stability properties of the points themselves. Why does it not make sense that you have an infinite number of equilibrium points for this mechanical system?
Because working region will be 2 pi linear.
Sorry?
Working region will be 2 pi.
Exactly. The fact actually that we said here that x1 is r is a misnomer. You're thinking that you actually have a state space that's Euclidean, right? You have a state space that lives in R and R. So it's R cross R. Is that true? That's not true. This is what the equation says, but that's not true. The actual state space is not from minus infinity to infinity in the x1 direction, and minus infinity to infinity in the x2 direction. This is the R2, right? R2 goes from minus infinity to infinity in one direction and minus infinity to infinity in another direction. So that's Euclidean. But that's not a Euclidean system. Actually has this idea of that minus pi is pi. So actually the true state space was not from minus infinity to infinity, it was only from minus pi to pi. One of them is excluded. Okay? So this was isomorphic to, remember? The circle, exactly, the unit circle. In that region only, how many solutions do we have? Only 2. One of them is minus pi and pi. So I have only, 0 and pi.
What if we linearize the system?
I'll come back to that. Okay? We're working with things non-linearly. Okay? Everything is non-linear. Okay? I'll come back to that later. So these are the only 2 positions so these are the only 2 solutions. These are the only 2, to be properly physical equilibrium points of the system. One of them is 0, 0. x1 is equal to 0 and x2 is equal to 0. How do you visualize this in the pendulum? The pendulum is pointing downwards, and is it moving? No, just fixed. What about the other positions? Upside down, and also not moving. Okay, so these are the 2 positions where. So this is the pendulum. So one of them is pointing downwards, the other one is pointing upwards.
Isn't
yes,
that an unstable?
We don't know. Stability and instability, we don't know. Yes. That's the whole idea. We just identify the equilibrium points. Whether they are stable or unstable, just look at it. And thus we have this MATLAB code, and let's play around with it.
What does equilibrium here mean?
Equilibrium, that's an excellent question. Anyone can answer that? What does the equilibrium point here mean? Yes.
The tangent at that point is equal to 0.
Excellent. So take 0 and 0 and plug it in back in the f. What do you expect?
F of x equal to 0.
F of x equal to 0 and thus?
x1 dot and x2.
x1 dot and x2 dot equals 0. So if you integrate this system, what happens to it? So imagine that you integrate x1 dot is equal to 0 and x2 dot is equal to 0. Given initial condition that x1 is equal to 0 and x2 is equal to 0. What is the result? What is the result of that integration? x1 is equal to 0 for all time, and x2 is equal to 0 for all time. Another example. Plug in the pi and the 0. In this equation, what do you get? Also 0 and 0. By construction. So integrate x1 dot is equal to 0 at given the initial condition pi. What do you get? x1 is equal to? No. What's the initial condition? Pi. So you start upside down, exactly upside down, and you integrate. Integrate means run time. Start the experiment. What happens to the pendulum? Stays there, exactly. It doesn't move at all for all time. So you integrate x1 dot equal to 0, given the initial condition x1 is equal to pi, then x1 is equal to pi for all time, and x2 dot is equal to 0, and the initial condition 0 is x2 is equal to 0 for all time. Clear what it means? Clear for everyone? So let's take this example. Okay, let's take this MATLAB code and just play around and let's see what happens. Okay. So we're just going to integrate the system. And play around with it. Okay. So thanks to ChatGPT, making these things are very easy now. Okay. By the way, this was actually a different layout. Just to fun story. This was a different layout. I just did it 3 minutes ago, before the lecture. Okay. Just I changed it from being text boxes like this to being sliders. Okay. So yes.
Why do you have 3 spirals. So let's say.
You don't have any spirals.
Why do you have three minimum points? So?
We'll come to that back. But do you see any spirals here?
Yes.
What is this actually? What are all these red? What is this red plot here?
This is the tangents. Vectors are on the map.
Exactly. These are tangent vectors at different points, exactly. And they are just the value of f of x at all of these different points.
F or f of x derivative?
No, f of x is x dot is equal to f of x, right? So x dot, the value of x dot, which are on these vectors. So this vector is, for example, this is x1 dot, x2 dot at that point.
Indicating instantaneous change, right?
Exactly. These are the instantaneous change. This is actually like the tangent vector at the tangent spaces. What is the tangent space here? This is the tangent space. That's why you see them in R2. The tangent space is R2, but the set space is not. And that's why we're gonna come. But I'm gonna come back to that later. So what we did here is that G is given by 9.8, the length is given by some number. The only thing we can play around with is actually just the friction coefficient. So you see here, I have some friction coefficient. So, and we can start from anywhere. So let's start, for example, from this location. Let's start the simulation for 5 seconds. So start from here, and this is the trajectory it follows. Is it clear that all the vectors are actually tangent?
Yeah.
Is it clear? To the path that you're taking. So this is, you see the blue one is actually a curve. Okay? It's actually like a curve, and the vector is always tangent to it. Clear? So now let's make this simulation a little bit longer because this is too short. Let's make it, I don't know, 15. Okay, let's reset and start. Okay. What do you think the asymptotic behavior is? So if you let time really run a lot.
Approach zero.
Converge to zero.
Converges to zero.
Approaching the equilibrium point. Which equilibrium point? Because it has two, right? It has 0 and 0, right? So this is, first of all, what you see here on the horizontal axis is simply the theta. What you see here in the vertical axis is theta dot. This is actually, does anyone know what this is called? It's already written there. It's called, the plot of theta and theta dot, or in general position and velocity, is usually called, it's usually called this is actually the state space. And when we add on it all of these arrows around which you're going to actually move to tangent to, we call this a phase portrait. Yes, exactly. So this is usually called the phase portrait. Okay.
Can we simulate this with vertical one?
Yes, of course. So let's do it. So let's, you want to start exactly at the vertical or a little bit near it? Exactly at the vertical. Now we're going to make it hard because we need to, let's see, we need to get 3.14 exactly. So let's start for 15 seconds.
It wasn't exact.
It wasn't exact. So this is numerical errors. Okay? So we will not get.
The rest of the numbers after 15.
Yeah, exactly. You can restart it actually to be, to be equal to pi. So you can make it numerically pi, but this is 3.14, which is not pi.
Yeah.
But what is the behavior that you saw here?
It stopped until it.
No. Did we start near? So first of all, where is this equilibrium point we're talking about? Do you see it already?
The starting point.
It's this one.
Yeah.
So you see, this was the first one, 0 and 0. The second one is
Here.
pi and 0. So 0 and 0 and pi and 0. So you see here, this is 3.14 something. Okay? So this is the pi, and this is the 0. When we started near it, what happened? It diverged from it. Maybe this was just a special case. If we start, let's try to start at the same point, but maybe go a little bit up. So with some initial velocity. We moved away from it, right? And we converged at 0 and 0?
But it went the other
Yes,
way.
it's 0, 0, but it's because
Is this 0 and 0 to you?
Yes.
It's not 0, 0. It's like, yeah, exactly.
It is because it's a multiple of pi.
Integrate multiple of pi.
The multiples of pi, right? You remember when we discussed, so first of all, when we looked at this first portrait from an analytical point of view, you say how many equilibrium points do we have? infinite. You have this one and this one. You have this one and this one and this one and so on. All of the multiples of pi. But this is an artifact. This is only a visualization artifact. Why? Because the true state space, actually, how does it look like? What's it called?
Torus.
Not a torus.
Can you say it's a cut piece of it?
So, first of all, when moving in this direction, this is the theta dot, right? Is theta dot from minus pi to pi?
No, it's
No.
from XR.
So the torus that you looked at, you remember last time when we looked at the manipulator, was actually theta 1 from minus pi to pi and theta 2 from minus pi to pi. This is different. This is not theta 1 versus theta 2. This is theta versus theta dot. So theta dot, what are the value? Where does it live?
Oh,
In R, from minus infinity to infinity. You can have any initial velocity. But the theta is the one that actually needs to be wrapped. So actually, we need to wrap the pi to the minus pi. So these two lines, they have to be curved and connected to each other. What's the shape that you get? A cylinder, exactly, or a tube. So this is the true shape of the state space. And if you actually plot the curves on the cylinder, you see that we do have only two equilibrium points. And this behavior that actually you start from one, you go away from one equilibrium point, you go to the other, will be very clear. So this is another artifact of just taking a manifold and trying to representing it by a chart. Is that clear?
And you can characterize this system as globally vertically stable.
That's an excellent question. So now we did not do any formal proofs, but by running, you can take the simulation home, play around with it as much as you want, and you can characterize now the two equilibrium points, this one and this one, as, is it stable? Is the 0 and 0 stable?
Yes.
Yes, it's stable. Is it asymptotically stable locally?
Yes.
Okay.
Locally,
Is the other one, is the pi and 0, is it stable?
No.
Is it unstable?
yeah.
By definition, if it's not stable, it's unstable, you remember?
Yeah.
So if it's not stable, then it's automatically if it's not stable, it's automatically unstable.
Not stable.
Because when we start near it, it will always diverge. Try as many as possibilities as you want. Try to initialize this as many as you want in anywhere near it. Even go as close as possible. You already tried that, right? You went 3.14.
But
Close.
mathematically, like this is like a physical, a visual analysis. But mathematically, why is it unstable? Like even if it's very close, naturally, shouldn't it go towards that?
So upside down.
Yeah.
So if you imagine that you have a pendulum,
No, it's a
and you start, you're talking about you start 3.14 exactly, so at pi exactly or a little bit slightly.
Because I'm saying that natural behavior should be when it is starting close to stable or equilibrium point, it should come towards that naturally.
Naturally, with gravity, without any control.
This is a physical aspect of that.
Are you sure? So take a pendulum, take a pen, and start it like this.
Like we can see this visually.
Will it go back?
It wouldn't.
So?
We conquer this visually.
That's right.
Physically. But how does that expression of x dot or x, like for example, if we couldn't physically verify it,
Yes.
how could that expression show us that this
That's an excellent question.
behavior?
So I'll repeat what Norman is saying and rephrase it. So here is actually because we are either maybe looking at the physical system or we are simulating it numerically and looking at different conditions. How can we actually just look at f of x and say that this equilibrium point is stable and this is unstable? That's exactly what we're going to be doing with the Lyapunov method. That's exactly what we're going to be doing next. Okay.
About the space that we call the tube, does it have an actual name, like a
Cylinder.
That's it?
Cylinder.
Does it have a representation like an S or a T?
It's S1 cross R. Exactly what we wrote. So you have a circle and it's elongated by an R. That's exactly what a cylinder is, right? Cylinder, and then you extrude it with R. And what about the torus? It was a cylinder, it was a circle that you extruded as another circle, so you get the torus. Clear? Going back, so this is unstable, this was stable. Okay? And it was asymptotically stable. Back to Tariq's question, is this globally asymptotically stable? Why?
Because there is only one equilibrium point that can
It will always go back to 0, 0. Like to always go back to the starting point.
So anyone can.
I think
It's global because the other equilibrium point will converge to
Cannot
It's
be
always, no matter where you start from, no matter how much.
global stable. It means that all the equilibrium points can reach stability.
No,
Here,
that's
it's
the
So
point.
it's not global.
That's
Not global. Why?
Because we can,
Ah.
this is a case where why is it not global? Because over here you can see it got to a shift in equilibrium point, not the same.
That's an artifact of the R. Of we're actually plotting the state space as R. So it's actually this equilibrium point is the same as this one.
So if we are interpreting it is like that,
Yeah.
then it will be global.
But that's true.
It's,
That's already the case. Yeah.
it's not global because there is 2 points or 1 point that you can start at.
Absolutely. That's the correct answer.
Where
It's not globally asymptotically stable
It's almost global.
because that's exactly how it's called. Yes. Okay. So I'll repeat. It's actually not globally asymptotically stable because the definition of global asymptotic stability means that you start anywhere on the manifold, you converge to that point. There is one point here I can actually start at, and it will not work.
Because we did not include one by we made that square, instead of square bracket we use that circle bracket.
I can exactly, but I can start at the pi, and then it will not converge.
But if that bracket was also a square bracket, then it will be globally asymptotic, right?
If you have that square bracket, it means you have 3 equilibrium points. You have 0 and 0, pi and 0, and minus pi and 0. But that's not true. You have only 2 physical equilibrium points. So if you have, so the bottom line is that if you have actually multiple equilibrium points, by definition, it's not possible that you have global asymptotic stability. Always.
Okay.
But the formal way of saying it is that if we exclude the equilibrium points and start
And
Okay.
other ways.
in other places, then let's put it another way. If all other equilibrium points are unstable, then if I start away from them, not exactly at them, but I start away near them, then actually you have the intuition that you have. I'm going to actually, eventually go to this locally stable equilibrium point. Okay? And thus we call it exactly almost global asymptotic.
Doesn't equilibrium point itself say that it should be stable?
No. The equilibrium point by itself means if you start at it, you remain at it. Not if you start near it, you go to it. That's a different thing. That's right.
If we didn't have the damping term, would the same
That's the next question. And now we can play around with it.
be in a stable point still, or no?
So,
What was the question again?
We don't
So-
have a damping.
let me reset this. Let me go here. Okay. That's ChatGPT, so
We have to start at
is that, yeah, we have to wait.
It's gonna
Yeah.
keep rotating around the same.
So let's start here. So, no damping.
It keeps on rotating around the.
What is this called?
Ellipsoid.
No, what is this behavior called? Which notion of stability is this? Stable.
Semi-stable.
No, it's called stable. Remember what you said about stability? I start near it,
And stays here.
I stay near it. I don't diverge, I don't converge. I just keep on roaming around. The picture was said just keep roaming around. This is, I started here. This was the equilibrium point. I did not go to it. I did not go away from it. I just kept on oscillating around.
To be stable, shouldn't I reach the equilibrium?
You should. This is the definition of asymptotic stability, not of stability.
So that stable is not practically possible.
Theoretically, yes. Practically, no. Yeah. So theoretically, yeah. So all of these are just theoretical notions of stability. Any more questions? Clear? You have the animation at home. You can play around with it, and if you come up with any questions or something that's not clear, just let me know in the next time, inshallah. So now this is the conclusion. So now we found that we have 2 equilibrium points, 0 and 0, pi and 0. This one is almost global asymptotic stable, and this one is unstable, provided that you don't. That's right. But when is this global asymptotic stable?
When other one is unstable.
No.
No, when there is friction.
When there is friction. If I don't have friction, this becomes unstable. This becomes stable. Okay. So now let's look at. So answer Norman's question. Now, so this is just simulation, right? So I cannot just always do simulations and actually plot. Actually, this phase portrait is very limited, right? Because it only works in 2D. Right? Because I always have, actually it always only works for 1D. Because if I have a 1D system like the pendulum, its state space is 2D, because there is x and x dot. Sorry, there is theta and theta dot, the configuration and the conversion dot. So I already have 2D. So I can plot a plane. If I have a 2D system, for example, theta 1 and theta 2, then the phase space will be 4 dimensions. It will be theta 1, theta 2 dot, theta 1, theta dot, theta 1 dot, theta 2 dot. So it's already 4D. I cannot already visualize it. Actually, this is too limited. This is only for toy problems.
But we can use a face portrait for a combination of different states.
Okay, then we're going to go through a lot of effort just to visualize a 2D system.
Can't you visualize it in 3D?
Do whatever. Then the best you can do is two-link manipulator. Okay. So, but this is not what actually we use. Okay. So what we actually use is Lyapunov theory. So Lyapunov is a Russian mathematician. Okay. He's infamous. Okay. So in any textbook you'll find his work, and he came up actually with two very simple, not simple, but two very powerful, methods actually to study stability of mechanical of general nonlinear systems. The first one is called the indirect method, and this is Muhammad, linearization. Okay, so just linearize around the equilibrium points. The other one is no, don't linearize. We can do things non-linear. Which one do you think we're going to be doing? The second one, of course. Okay. The first one I'm going to only mention it only for your curiosity. If you've seen it before, then you know it. If not, this is only actually read only. Okay. And we're also given with some supplementary material that you can actually play if you want to practice this method. Okay? I'm not saying this is nonsense. It's actually very powerful. I'll tell you why in a bit. So the whole idea of Lyapunov's indirect method, okay, is that simply x dot is equal to f of x. I can linearize it around the equilibrium point. If I linearize it, then it becomes what? A linear system. If x itself was the state, then I can define a new state called z, which will become x minus x star. And you see here there is a minus here. What does this minus mean? What does it imply? Small deviations, that's correct. That's one thing. So it's only very near the equilibrium point valid. But it also implies that x actually has a vector space structure, right?
Okay.
So you see here, this is why the linearization is only properly written this way is actually only in Rn, okay? But you can also generalize it even to a geometric setting. But this is only, the Rn version. So x minus x star, this is the z, and then I can define the dynamics near the equilibrium point. But near here means very near, just very close to the equilibrium point, as z dot is equal to az. So z is the new state, a is now the Jacobian of the f. So the Jacobian is simply partial derivative of f with respect to x1, f with respect to x2, and so on and so forth. Every partial derivative actually is just a column. So f1, okay, partial f by partial x1 is this element, partial f by partial x1 is all of this vector, partial f by partial xn is all of this vector, and so on. You just concatenate all of these elements, and you call, and not only that, you have to substitute the equilibrium point. So if you evaluate the Jacobian at the equilibrium point, what you get here is just a constant matrix. So this is the simplest, toy problem that you can always. You're all very well practiced to actually play with this. It's just a linear system that has a constant A matrix. Okay? What do you do with a linear system? No? Eigenvalues of the A, exactly. You just compute the eigenvalues. How many eigenvalues do you have?
Based on the number of states.
Based on the number of states. How many states do you have? What's the dimension of x here? The dimension of x is n. So I get n eigenvalues. And then you just look at the eigenvalues. First thing you do, if any of the eigenvalues has a real part greater than 0, immediately the equilibrium point you're talking about is unstable. Directly. That's very easy. Second thing, if you have, that's this one, if all, and you see here the notation here. I'm saying here any, but here I'm saying all. All eigenvalues, they have the real part to be negative, means that locally asymptotically stable. Okay? And if you have any eigenvalue with a real part that's equal to 0, any eigenvalue with the real part equal to 0,
Imagine a state.
no.
Need more
What did you say?
information.
Need more information. Exactly. In other words, the indirect method stops, fails. It cannot say anything. It's inconclusive. Okay?
What does inconclusive?
Inconclusive means the method cannot tell you whether it's stable, unstable, asymptotically stable, globally asymptotic. It cannot say anything.
But in linear multivariable control, we used to call it.
That's an excellent question. Can anyone answer that? Why, if you have a linear multivariable in the linear multivariable control course, you actually concluded that it's marginally stable?
So in the linear course, we are talking about strictly linear systems.
Absolutely. So the correct answer is that the systems you started with there are actually linear, not a linearized version of a nonlinear system.
Actually, if you linearize the system,
Sometimes we use linearization.
That's an excellent point. Then if you linearize the system,
Then it's not conclusive.
and it's inconclusive about the nonlinear system. You see here what we're doing? This is actually very powerful. This is what you see what we're doing here. We took a nonlinear system, we linearized it, we studied the properties of the linearized version, and then we're concluding properties of
The nonlinear.
the nonlinear system. So this is where it fails. Okay? If you conclude something from the linear to the nonlinear, in this case it's wrong. Okay. This is, so you see here, X star is unstable for the nonlinear system, and this is X star is locally asymptotically for the nonlinear system. Okay. By the way, this simple theorem, which just fits in, in a half a page, is actually the main reason why people doing only linear control work. Okay? Why linear control works for nonlinear systems, right?
Yes.
That's the only reason.
Yeah.
Okay? So they're very lucky just because of this theorem. Okay?
I have a question.
Yes.
So is it locally asymptotically stable because we're just checking one point, or is it because it's a nonlinear system? For example, if we took all equilibrium points,
Yeah.
and we found that we linearized all of them, and we found that all of their eigenvalues are less than 0, could we say that it's globally a stable system?
How come? First of all, how come you have all of them to be locally asymptotically stable? That's actually not even sometimes possible, right? If all of them you start near them, imagine this picture. I have two equilibrium points. Okay. All of the trajectories I start here near it have to go this way, and I have another equilibrium point here. All of the trajectories have to go this way.
Okay.
What does this leave in the middle?
Hill.
Right? So imagine all of the vectors pointing this way and all of the vectors pointing that way. If you have a smooth vector field,
Unstable, I think.
there has to be something unstable in the middle. Exactly. Between the two stable equilibrium points, there has to be an unstable one that actually pushes away the rest of the two. This is what I just mentioned here is actually this is a whole topic on its own. You can actually go really deep into this stuff and actually can take a course on nonlinear dynamics. Okay? So nonlinear systems and nonlinear dynamics, they really dive into this stuff. And then you can go into chaos theory, and there are very, very nice stuff there. Okay? There are nice stuff online if you want to watch, if you have time actually. Okay. So now this is the animation is a little bit messy, but this is Lyapunov's direct method. So we're not going to be dealing a lot with Lyapunov's indirect method. It's very powerful. Okay. The only power actually of it, in my opinion, is that actually it's a very easy check for
Stability.
no.
Linearized systems.
No. It's a very easy check for
Controllability.
nope. We haven't talked about controllability and observability. It's a very easy check for unstable points. If you want to check whether a point is unstable or not, just use Lyapunov's indirect method, right? Because it says that, you remember?
Isn't it the same as stability?
No. Just the instability itself. So if you want, and that's actually one of the examples that you can have in the supplementary homework, take the pendulum, linearize it about the top equilibrium point, and check the eigenvalues. What do you get, do you think?
Positive 1 and minus
One of the eigenvalues will actually be positive, which means immediately, it means immediately without solving the system, without integrating it, it's actually unstable. That's the easy check about. Okay? And computing the Jacobian of a nonlinear function is very easy. MATLAB does it with one line. Okay? So it's really easy. And even numerically, it's even possible. So this is the Lyapunov direct method. Who's familiar with it? Who's familiar with this method? 1, 2, 2. Okay, all X. Okay. Lyapunov's direct method is the following. Okay. So Lyapunov came up with this idea. Okay. It's very powerful, but it's actually very obvious, by the way. And I'll tell you why in maybe not this lecture, but next lecture. X naught is equal to f of x. That's the system you start with, non-linear. Lyapunov's direct method works with the non-linear system. There's no linearization. It says that x star is an equilibrium point of the system, so you already need to know which equilibrium point you're talking about. And then it tells you, you can classify the equilibrium point as being either stable, asymptotically stable, or globally asymptotically stable, if you can find the following. And this is the theorem. If you can find the Lyapunov function, so what do we mean by Lyapunov function? It's a function that satisfies the following properties. It's a function of x. So it's a function that goes from x to r. Okay? It's a smooth function that goes from x to r. First of all, that when you evaluate it at the equilibrium point, you get 0. Okay? That's the first thing. The second thing is that if you go away from the function, okay, in a small region, the function is always positive. These two conditions together, they actually mean that the function is what's known as a positive definite function. Okay? So, but not only that. So not any positive definite function is a Lyapunov function. We need to actually calculate the derivative of this function along the system dynamics. And what do we mean exactly by that? That's next lecture, inshallah. So v dot of x is evaluated when you plug in x dot equal to f of x. Okay? So you see the v of x is actually independent of the dynamics, but the v dot includes into the dynamics. You just take the dynamics and you plug it in the v dot. And you have to check whether this function that we calculated, the new function v dot, is always less than or equal 0. It can be equal to 0, okay, or it can be less than 0, but not greater. So it cannot increase at any point. And this is actually a definition of what's known as a semi-definite, negative semi-definite function. Question.
I was about to say that, so you're saying that we take f, we substitute it into v dot, correct?
You take the v,
Yeah.
you calculate its derivative,
Yeah.
and its derivative will actually have x dot entered.
Okay.
So you plug in x dot is equal to f of x.
Somehow.
It's very easy. This is what we're going to be doing next time. So we're going to complete it later. But today, just try to understand the abstract picture. Okay. So if you can, so here, does it tell you how to find the function?
No.
Just tells you choose any function and prove and show this. What can you conclude about this, the equilibrium point? That it is stable.
Okay.
So in order to make it from stable to asymptotically stable, we have the exact same conditions, but they have to be a little bit stricter. What do you think we need to make stricter?
Derivative is always decreasing.
The derivative should be always decreasing. It should not be equal to 0 at any other point except the equilibrium point that you're talking about. Exactly.
So it's a problem.
We'll come to that later. If you want to check for global asymptotic stability, you need to make it more stricter. So it's not enough that it's equal to 0 at the equilibrium point, and that it's positive definite, and that it's also the derivative is less than 0. You need another condition, and this condition is usually called that the function is radially unbounded. Radially unbounded means that I keep on moving to x equal to infinity. What do I get? I find that d is infinity there. So as x, so what this is the norm. So x minus x star, it means that is the norm, the distance away from x star. As this goes to infinity, so it means that as x goes away from the equilibrium point in any direction, along x1, along x2, along x3, along, combination of x1, so in all directions, you can imagine like a circle, a hypersphere that goes everywhere, starting from x star. You find that v of x, which is this function, the scalar function, should reach, its limit should be infinity. Yes.
Okay. For it to be globally asymptotically stable, we only need one. The system has to only have one equilibrium
Absolutely,
point.
that's correct.
So why don't we just check for if it has only one equilibrium point, and then we could see if it's asymptotically or globally asymptotic.
That's the next question. It could have one equilibrium point, and then it can be locally asymptotically stable, not globally. Okay?
It has to have another equilibrium point.
No, because you can start near the equilibrium point, and then you can go near to it in a region. But if you start away from it, you don't go anywhere.
Won't v of x always goes to infinity?
Nothing happens.
You just blow up,
Okay.
It will diverge.
You blow up.
diverges.
You stay.
No, you diverge.
To diverge, there should be a different eigenvalue that's positive. There needs to be-
There are even trickier ways to say it, because you can even go to another structure there. You can go to something called the limit cycle, but things get weird there.
As x goes to infinity, v of x will always goes to infinity too.
That's not necessarily. I'll give you an example to show to see that. Not necessarily, because we're saying, you remember, look at the theorem. The theorem says any function, so I can always cook up, some weird function that actually, that doesn't go there as you go to fit. And I'll show you an example in a bit. Okay. So that's the theorem. Very easy, very useless. Why?
Only for the linear systems.
No, it's
No?
Linear
We have to define what v of x is.
Exactly. It does not give any, recipe of how to do it. It just, tells you, find the v and then do it. I'll give you an example. What if I find the v and I'm able to conclude that it's stable? Does this mean it's not asymptotically stable?
No.
It can
Because
be
we-
the
Since it's less than
If it's asymptotically stable.
If I found the v, so I found the function v,
Yeah.
and I prove that it's stable, can I say that since I already showed the v and I showed it's stable, it automatically means it is not asymptotically stable
No, it can
and not globally asymptotically
It's
stable?
not
It can
exclusive.
be asymptotic stable.
If v of x is less than 0, it could be asymptotically stable and stable at the same time.
But
Yeah.
no,
If it's
Mm.
less, it's
Maybe the
Function,
function, maybe the
uh,
function itself, it's not right.
The tag is not
Exactly.
Ah.
Maybe for the function I chose, I'm limited only to show it's negative semi-definite. But if I change the function,
Yes.
someone else comes up with a smarter function, he can actually show asymptotic stability.
what do you mean come up with another function?
This says find any function.
But here it's
If you can find a function that satisfies this, you can conclude stability.
but here v dot of x can be less than or equal 0.
For this v,
Okay, but
for the v I chose. Someone else can find another v, so v1 and v2. v1, you use it, you evaluate the derivative of it, you find it's negative semi-definite. You conclude stability.
But if
But
v
you can't
dot of
conclude.
x equals 0, that means that it will be not asymptotic stable.
v1 or v2. You see?
So basically what you're saying that two people can do the same thing but arrive at different conclusions.
Absolutely.
Basically.
Yes. Because they started from two different functions.
Yeah, it's not that something is weird with the V. It's just that
That's the choice of v.
the choice of V led them to the conclusion that it's
Absolutely.
stable, for example.
Exactly.
For example, I choose one function, the stable criteria fails. You choose one function, stable criteria meets.
Yeah.
Both can be right at the same time.
Yes? So if I find a function that satisfies this criteria,
Stable.
automatically it's stable.
Yeah.
But you could have chosen another function that you're able to only show this criteria.
No, but if I choose a function that does not fulfill the criteria of asymptotic, for example,
Yes,
and you choose a function which fulfills that criteria.
absolutely.
So for me it will be unstable.
No, for you it will be, for you, you have a proof that the equilibrium point is stable. And I have a proof that the equilibrium point is asymptotically stable. And my conclusion, so my result implies yours, but not vice versa. So if I'm asymptotically stable, it means automatically I am stable. But if I'm stable, not necessarily that I'm asymptotically stable. Okay.
I think
Yes.
what Roman actually wanted to ask was that there is a possibility that someone comes up with a function that shows instability of the equilibrium.
That's a very good point. Do you see any instability here?
It's the point.
No.
It's not possible.
We already said that we can check the instability from the indirect method.
That's right. The instability you can use it from the indirect method, but Lyapunov's direct method can only show stability, not instability.
So it's inconclusive about instability.
It cannot. There is none of this actually. There is no recipe that you can do.
We cannot say if, let's see, we choose a function and if it's not even a negative semi-definite or it does not, it's a, let's say it's a positive definite function, but its derivative is not negative semi-definite, we cannot say that the equilibrium
No,
is unstable.
no, exactly.
You can't find another gate that might. You can't
Exactly. No.
Not conclusive.
Absolutely. Yeah. You cannot. So in other words, you cannot check for instability using Lyapunov's method, for the direct one.
But you can still go to the eigenvalues, right? So
Yeah.
Why can't you?
That's an excellent question. Anyone wants to point out? So why cannot I just use the indirect method to check for the instability?
Equal to 0.
I might have one of the eigenvalues equal to 0, and thus I'm inconclusive. Imagine that you have a 1,000 by 1,000 system,
Okay.
and one of the eigenvalues, 199, they are negative, or so 999 they are negative, and one is 0.
If I have the eigenvalues, why do I even need to go to the Lyapunov direct method?
Because the indirect method is actually
Only states stability, but this can show me asymptotic
What type of stability?
here. This says actually you can check for asymptotic stability and global.
Okay.
The other one does not have global.
It just says it's stable or not.
It said it was either unstable or asymptotic stable locally.
Okay.
Even stability cannot say it. So in other words, the indirect method. So you need to go back to the slide. So take a look here. What are the checks that you see? Unstable and local asymptotic stability. Do you see stability here? I cannot check for stability.
Local asymptotic, so it's stable.
No, but that's already local asymptotic stability.
Mm-hmm.
There is no case here that you can conclude from it it's only stable.
But
Don't get
we
it.
have local
If it's local,
we don't
Like
stability.
we just saw on the next slide that if it is asymptotically, then it is stable.
That's right. What I'm saying is that you do not have the case where it's stable but nothing else.
But we said the case that if we have
Why?
asymptotic, then it is stable.
That's right.
Why
What
do
I'm
you
saying
say
is that it does not have the case where it's stable yet.
Okay.
You see?
Yeah.
So if you want to check,
So
so what I'm contrasting here is the limitations of the indirect method.
So you're saying if it's 0, it can be stable only.
If it has here
Yeah.
one of the angles is equal to 0,
It can be
it's
stable.
inconclusive, which means that it could be stable or unstable, or so on and so forth. It can be many things. You cannot say anything about it.
What if it's unstable? How would we know?
So let me rephrase it. If it was Lyapunov, if Lyapunov's indirect method told you it was inconclusive,
Yeah, and we know it's.
and you want to check for instability, what should you do? Other methods.
Okay.
And they are usually harder than Lyapunov's arguments. Actually, it's harder to prove instability than to prove stability. If the indirect method fails. If the indirect method fails.
We assume that for the next slide, the direct method always works. Like we will always find that Lyapunov function that is at least stable.
Maybe yes, maybe no.
How can we prove instability?
No, stable.
Usually it's the other way around. So think of why actually we're doing this. Why actually we want to use Lyapunov's direct method? What's the main reason why we want to do it?
We can't find the eigenvalues.
We want to check what kind of stability it is.
And I mentioned something about when we're actually going to be checking the stability, what else we're going to be doing along the way?
Controller.
Designing the controller, exactly. So if you're designing a controller, do you want to prove it's stable or unstable? Not only stable. Stable means that I start from some initial condition, the error will keep on roaming.
Asymptotically stable.
Asymptotic stability is always the minimum requirement. Locally, local asymptotic stability is always the minimum requirement. Global is even better, and there are even better stuff because you want even to converge very quickly to the equilibrium point, and then you can go to exponential stability. You can even go to what's known as finite time stability, where it's with sliding mode stuff and so on and so forth. Okay?
Make sure that all the states are controlled.
That's a completely different story. I'll ask that again. Yes, Asha.
No, continue.
Yeah, go.
Who's first? Yes,
Okay, so sir, if we are able to find a Lyapunov function that, for example, satisfies the asymptotic stability, it means that for all the eigenvalues, even if we have one that is equal to 0, it's not unstable.
Again, could you repeat the
Like if
question?
we find the Lyapunov function.
If you find the Lyapunov function, you do Lyapunov's direct method,
Yeah, this asymptotic stability.
you conclude that.
Yeah, it means that for all the eigenvalues in a particular system, everything is stable.
No, wait a second. There's a lot of assumptions there. Let's take it step by step. You have a system. It has multiple equilibrium points.
Yes.
You want to check the stability of only one of them with this method.
No,
You see here?
the entire system. Let's say we are considering the entire system.
That's not possible. And this is something we discussed last time. There is no such thing as stability of the nonlinear system.
We can only do it about a particular point.
It's always stability of the point, not of the system.
So,
Even if you linearize, you're linearizing around the point.
That's what I'm saying, that point is going to be the point where we are going to linearize that system.
Exactly. And here, the point is already the one you evaluate the Lyapunov function at. So it's always the stability of the equilibrium point. There's no such thing as the stability of the system.
If we change that equilibrium point, then
Yes.
it might be stable, unstable for that.
So rephrase think about it in a different way. Don't think about the true nature of the point itself. Think about what you can conclude from the Lyapunov function. So I'll rephrase it in the following sense. I found the Lyapunov function, and let's take the pendulum. Point, downward position, upward position. I choose the Lyapunov function, evaluate it, and I find that the downward position is locally asymptotically stable according to this criteria. And then I take the Lyapunov function, same one, and I plug in it the top equilibrium point, and I find that I cannot do anything actually here.
So does that
I don't even have a recipe for instability, so I cannot say.
can't even find the function.
There is no recipe. Lyapunov's direct method is only for stability, not for instability. If you want, you have to do another. You have to come up with. You have to cook up some sort of other way of checking stability.
As far as I remember, the original Lyapunov theorem, it states that if a equilibrium point is not stable, it is unstable.
Are you sure?
Yeah, that's what I remember from the theorem of the Lyapunov.
Okay,
Then that
I'll counteract that statement. So you find the Lyapunov function, and you cannot show that it's actually stable. And next room, and I find another Lyapunov function and I show it's stable. Who's true?
The stable one. Because you need only one to prove that it is stable.
Exactly.
But we are talking about the methods of Lyapunov. We are not talking about the Lyapunov's theorem. I'm talking about the original Lyapunov theorem.
What's the original theorem?
The theorem, it only relates to the nature of the equilibrium point itself.
Okay, so that's actually not a theorem. What you're talking about is actually the stability notions we discussed last time. So some people call a stable equilibrium point, they call it stable in the sense of Lyapunov.
Yeah.
Okay. But that's the definition. There's no check or anything. But there's actually no theorem there, and you don't need to plug in Lyapunov's name there. It's just stable. That's the point. Okay. So let's stop with the questions. We still have. Let's see how much we have here. Actually, not a lot. Let's try to very quickly go over them. You also came late, so I'll take some minutes from the break. So we need to look a little bit closer on what are positive definite functions. We said we need to choose one. We need to choose them, but what are they? Okay. I'll show you some pictures, and then they will make sense, right? This is the positive definite function. Scalar function of x. So va1 of x is equal to x squared. What does it look like? It's 0 at x equal to 0, and it's positive everywhere away from it.
Yes.
Does it satisfy positive being positive definite?
Yes. And it's always decreasing.
And it's always.
The slope is always
It's not about the slope. The slope. No. Okay, I see your point. You're talking about the v dot, right? There is no v dot here. There's only the v.
It is here, but it's not represented.
No, it's not here at all.
Why?
Wait for next lecture.
Okay.
I'm talking only about the v here. Don't confuse the v with the v dot. Only the v here is positive definite.
He has one lowest value possible.
We have one exactly. We have one.
Lowest value possible.
What do we remember? What we call it?
Equilibrium point.
It's around the equilibrium
What is this point of the function called? Remember? It was called the critical point. Remember? Critical point or extremum of the function,
Okay.
right?
But
Where
to the theory, we have to find the v dot to say it's a positive or negative difference?
No.
No, no, no.
I'll go back here again. The theorem says find the v that's positive definite. That's the first criteria. And then evaluate its derivative at the dynamics, along the dynamics, and check for stability. So the first, today's lecture, we're going to only, in the next 5 minutes, we're going to only stop here. What is the positive definite function in the first place? And then how do you evaluate it next lecture? Okay. So this is the V, this is an example of a positive definite function. This is another example of a positive definite function. You agree?
Yes.
Positive
I
definite.
remember there was something that if we put value of that function equal to 0 and the function line crosses only once and then stays under that line, there's some sort of that sort of definition for positive definite. Is there anything?
If you say anything with plots, then you're already talking about 1D and 2D. This is only, wait, we're going to come to the real stuff, okay? So this is just, you know, it's a appetizer. So this is another function. Is it positive definite? Around the 0. So it's 0 at 0, and away from 0 it's positive.
But it's not positive everywhere.
It's not positive definite everywhere. So what do we call this? Globally positive definite function, and we call this locally. No. Locally positive definite. It's only positive definite if you consider the interval
From minus 2 to 2.
from somewhere, it's exactly from there, less than 2.77, or something like in here. Okay? So actually this point. So from minus 2.77 to 2.77. This is the region where it's actually positive. Okay? Make sense?
Makes sense.
So can we generalize this to do 2D? Makes exactly the same. So instead of having x1 x squared, I have x1 squared plus x2 squared. So it's two parabolas in both. It's a parabola in both directions. This is exactly the same function we looked at, okay, but in 2D. Make sense? Can you generalize this to ND?
Yes.
Makes sense. Now if you start to plot stuff, you know, and check for positive definiteness by being plotting, then you're actually talking about maximum of 2 variables, right? You're back to the case of I can only study, you know, system of 2 states. Okay? So now let's try to figure out the formal definition. You know? Let's go to real system. Now I have n states, 1000 states. How do I check for the positive definiteness of the function? These are the formal definition of what a positive definite function is. I'll just make it, it's just, you know, very intuitive. You need to read it, but it's just the slides are just scary a little bit. Okay? So a function psi that eats a point x and gives you r, so a scalar function on the manifold, is locally positive definite about some point on the manifold if, first of all, you evaluate the point, you evaluate the function at the point you get 0, and there exists some neighborhood that includes the point such that the function is positive for all points that are within the region excluding the point you started at. Nothing different. So this is what a locally positive definite is. It's semi-definite if it's not just greater than 0, it's greater than or equal to 0. That's positive semi-definite. It's globally positive definite if you can show that it's 0 for all manifold, okay? Excluding, of course, the point you add, the equilibrium point, so the critical point here. And it's locally negative or negative semi-definite if the minus of the psi is positive definite.
Minus. Okay.
If minus psi is positive definite, then it means the psi itself is negative definite.
It's inverted.
If instead of looking x squared, you have minus x squared. Okay. So, what are local minimum and local and critical zeros? So, a strict local minimum of this function is simply the ones that we're talking about. So, they are the ones that you increase in all directions moving away from it. And you remember that, okay, this is classical result from your calculus, that if you have a differentiable function and you say that x star is a local minimum, then you should evaluate x star at the Jacobian of the function, you should get 0. You remember when you had to calculate the gradient should be equal to 0 at the minimum and maximum points, all of these extremum. That's the same stuff. So in general, in ND, you just have the Jacobian, so we're back again to the Jacobian. And you see here, I have two conditions. The class of functions we're studying actually have that. Psi of the function is equal to 0, but also the Jacobian, okay, at the point is equal to 0. This is a special type of point. It's actually called the critical zero for the system. That the function itself is zero, but also the gradient of it is zero. Okay? So why is that important? You all heard about positive definite matrices, right?
Yes.
Negative definite matrices, right? What is the relation between both? Let's stop here. Okay, because that gives you some time to materialize. Okay, please study this before next time. Okay, we're going to be continuing, and I'll take some questions if you have. Yes, right.
If we have an inverted parabola that's shifted upwards,
Yeah.
do we say that anything above the x-axis is a positive definite? Any rearrange that?
No, positive definite means that you move away from it, you go up more than the value that you had.
Yeah, we have an inverted parabola, but it's shifted upwards. Like
But then the top is not zero, right?
yeah.
But one of the conditions just to exclude that is that you have to have the zero. Yes.
We may have a situation whereby the minimum point, the value of v or the psi function at that point is
Yep.
not zero.
That's right.
It is still the minimum.
That's an excellent point. Let's go back to the parabola actually. Take this point. This function, x1 squared plus x2 squared, and then add to it some c. So what happens to this curve? It goes up. So what's the Lyapunov function that you can define? So let's assume that the function that you're talking about was x1 squared plus x2 squared plus c. What should be the function I should use for Lyapunov?
Minus c.
The function minus c. So I just shifted back. You can always do that, right? So it's very easy check.
So there is some way, some rules to make this function. It's not just messy. It's not just with any node we can do this function, this v.
So usually what you're going to find, especially in control, the first choice is always the square function, the quadratic function, the parabola. Okay? If you took any course on adaptive control, this is usually the first thing you do. You do S transpose S. This is, by the way, x1 squared, x2 squared, in general it looks like x transpose. So x is a vector, it's x transpose x. You can even generalize it. You can even make it x transpose with some matrix in between, let's call it px.
In adaptive we used to go for 1 over 2 x squared.
1 over 2s squared if it's scalar, and if it's a vector it's half s transpose s. It's always the norm of it. So you guarantee that you have positive, that you guarantee that you have a Lyapunov function, and the controller that you derive will just satisfy it. You can always do that. Yes. Okay, so let's stop here. See you inshallah next time.